Hello everyone, welcome back to part 2 of the optimization of LLM performance series. Today let's talk about context engineering. Let's start with the overview of generative AI optimization. We have already know that LLM is an autoregressive next token generator. The prompt is the input X, the model is the function F, and the output Fx or Y is the probability distribution of the next token's candidates. To optimize the performance of the LLM, essentially we are optimizing the accuracy of the next token prediction results. To do that, there are two ways to do it. Either we optimize the prompt or we optimize the LLM. If you want to optimize for the LLM, we generally call it training or learning, depending on the aspects, how we look at it. Fundamentally, we are changing the functions and billions of parameters. As today, the models are generally very powerful. They're already well pre-trained and fine-tuned with the archive of the internet. Instead of working on improving the model, we can work on improving the prompt that is input into the model. There are two notions that I want to mention here. The first thing is called prompt engineering, which essentially the techniques to improve the structure and phrasing of the prompt. And here there's a new concept that is introduced not long ago, which is called context engineering. The task is to give relevant information to the prompt that allows the LLM to understand it better. Before we go into either of that, we will talk about in-context learning, which is some prior knowledge we should know before we talk about the prompt or context engineering. In-context learning is a technique where task demonstrations are integrated into the prompt. This approach allows pre-trained LLMs to address the new task without fine-tuning the model. Here is an example. We can see that this part is the prompt all the way until output, the black color text. And the earlier parts are the examples given before the requested input. Here we call these in-context examples, and the final input being the test example. If we pass these parts into a pre-trained LLM model, the model will be able to generate text that follows the content and format of the examples given. Now let's talk about how in-context learning works. While the model performs tasks by conditioning on input and output examples without optimizing any parameters, the model uses the prompt to locate the latent concepts acquired during pre-training. Let's say here we give these three examples before we ask the LLM to answer this query. The LLM will then try to infer and retrieve concepts such as financial news sentiment that it was trained many times and seen in the training data. And then by looking at the format and the content, that means the correlation between the answer and the example prompts. The LLM will then decide the the answers format as well as the latent concepts in the process. This process of locating learned capability can be viewed as a Bayesian inference of a prompt concept that every example in the prompt shared. This is the generalized formula, which I won't expand further. There are, there are generally two types of in-context learning. One is called zero-shot learning, and the other is called few shots learning. Here is an illustration of zero shot and few shots. By saying zero shots, that means we are not giving any example for the LLM to refer. Instead, we only give the instruction for the LLM to follow. Whereas for few shots learning, We give one or many examples for the LLM to learn, and then we pass the intended query for the LLM to generate its response. Here are some examples of zero-shot prompting. Essentially, we only describe the task and provide relevant information without examples and let LLM to follow our instruction to do the task we want. Say for sentiment analysis, the prompt can be to ask LLM to classify the text into neutral, negative, or positive sentiment. And the LLM will output the sentiment to be the class that it desires. And we can also ask the LLM to reason, like to solve a math equation of the sum of 7, 3, and 5. The LLM will then answer directly with the solution it thinks it is. On the other hand, for few-shot prompting, we will prompt the LLM by instruction, which serves as a context and examples. Here, when we do sentiment analysis, we can give the instruction to classify the text into neutral, negative, or positive. Then we provide some examples of what text is considered positive and what text is considered negative, so that the LLM will be able to answer more accurately for the sentiment classification on the given text. With the knowledge of in-context learning, now let's talk about some prompt engineering essentials. Before we talk about each principle of prompt engineering, we should keep this at the back of our mind that we should always treat LLM as our newly hired personal assistant. And personal assistants generally possess great general knowledge with certain level of breadth and depth. And the person is capable of understanding our instructions and think logically on their own. And the person is able to learn to proactively use tools that are made available. And finally, but very importantly, the person cannot read your mind. When you give instruction, you should be very specific and very detailed and explain some rationales where necessary. Now, the first principle we should follow while doing prompt engineering is that we should be explicit with our instructions. That means we should include as much details as possible in our query to get more relevant answers. Now, let's look at some examples. One bad way of asking LLM for information is to stay very high level. That means if you ask the LLM to tell you about cars, LLM will not know how to start. It will only guess what you may want to find out. But if you give more detail, like if you ask LLM to give you the key features of electric vehicle that is manufactured in 2025, LLM will be able to guess your intents. Potentially, it may think that you may want to buy an EV soon, or you may want to check the prices of the EV, or you may be considering changing a car. The LLM will then generate the response that could be closely aligned with your unmentioned intent. Another example would be here. If you ask the LLM to describe the features of a new iPhone, it could be very general. We can give more specific instruction, such as how long we want the answer to be and what kind of detail or what kind of tone the LLM should use. If you ask it to explain to a high school student, the words or the phrases used will be simpler. The second thing to do is to provide context to the instruction. Instead of only asking LLM to not do something, we can explain the rationale or why we ask the LLM to do so. One example is that instead of asking LLM to only never use ellipses, we can tell LLM that your response should be to read aloud by a text-to-speech engine. Never use ellipses since the text-to-speech engine will not know how to pronounce them. Now that the LLM knows the rationale of why this shouldn't be done, the LLM will then follow more closely and potentially it can extrapolate your request to not do some other practices also. The next principle will be using symbols. Okay, there are some symbols that LLM have seen many times when it was trained. triple double quotes, like the triple equal signs or the triple hashtags. These are symbols that appear in code or in markdown format repeatedly. Potentially, if you want the LLM to debug some piece of code for you, you can first start with the instruction and then you use some XML style tag to enclose your code and enclose your error. The LLM will be able to know the structure of your prompt more easily. The next one is to specify the output format because when you build an LLM application, you may want to have your generated output to be more controllable and usable instead of just free text. You can ask the LLM to generate the content in a table with columns. You can treat it as a CSV and use the some related SDK or library to handle it. You may also ask the LLM to generate a mind map if you are doing some ideation. By specifying the output, it helps us conduct practical tasks more effectively. Next, if we are an expert of the task that we want LLM to do, and we know pretty clearly the steps it takes to complete the task well, we should specify the format or structure of the text. The next one is to specify the steps. If you are an expert in the task given to the LLM, you should specify the steps that is required to complete the task. For instance, if we were to write a blog post on the recent advancement of AI, we can specify how we want the LLM to do it step by step. Here, we may want the LLM to craft an outline with 3 to 5 section headers, and then to write 2 to 3 arguments for each section, and then convert the arguments into 100 to 200 words. And finally, we ask the LLM to write an introduction and conclusion in 100 to 120 words each. The next one is to assign a role. If we want the LLM to answer some specific questions in certain domain, we can ask the LLM to role play an expert in the domain. For instance, if you want to ask the LLM to answer some quantum computing questions, we can ask the LLM to role play a quantum physicist. Or if we want the LLM to give us, say, a training plan or maybe or gym plan or dietary plan, we can ask the LLM to act as a certified personal trainer. By giving a role, LLM will be able to role play the role and generates more effective response for us. Now is a break. Yeah. The next part, we will talk about reasoning. Essentially, these are some ways that LLM are trained to conduct extended thinking or do long distance reasoning or planning. Now let's dive into it. There are multiple reasoning models for different series of M's. Nowadays, for OpenAI, there are GPT-5, which is a reasoning model, and they also offer a GPT 4.1, which is a general model. For Anthropic, it offers Cloud Opus 4.1, okay, which is a reasoning model, and CloudNet. Recently, it was just introduced 4.5, which is the most powerful general model. And Gemini, there is Gemini 2.5 Pro, which is a reasoning model, and Gemini 2.5 Flash, which is general model. And for DeepSeek, there is DeepSeek R1 series, which is a reasoning model, and the DeepSeek V3, which is a general model. We can see when we interact with the LLM applications, we can choose the respective models based on our task. So this is a screenshot for Cloud, and this is one for Gemini. So essentially, for reasoning models, for an AI agent, reasoning models are the brains to think, observe, and validate, whereas general model are the hands to execute. In the context of LLM agents or AI agents, reasoning models are the brains that help the agents to think, to observe, and to validate, whereas a general model are the hand in the context of a reasoning In the context of AI agents, reasoning models are the brains to help agents to think, observe, and validate, whereas general models as the hands to execute tasks for the agents. The first model, which is the simplest model we will introduce, is called prompt training. Prompt training enhances LLM's accuracy, clarity, and traceability. Tasks get more complex, such as writing a blog post. The performance of the goal of prompt training is to enhance LLM's accuracy, clarity, and traceability. For complex tasks that have multiple distinct steps, where each require in-depth thoughts, we will apply prompt training to prompt the LLM one step at a time. Here you can see that given a task, we will we will write a prompt and pass into the LLM to let LLM to make one gen response. And with the response, we will pass another prompt to do another inference, and then we will pass it to do the another inference, and so on. Essentially, it breaks a single prompt into multiple sequential prompts to enhance the LLM accuracy, clarity, and traceability. Here is an example. Without prompt training, we will only ask the LLM to say, create a research plan for the topic of AI-aided learning enhancement in K-12 schools, and the LLM will generate the answer directly. But if we break this task into three distinct steps, where the first step, we ask the LLM to search on relevant articles, and then based on the finding, we let the LLM to proceed to craft a meaningful research question. And after the LLM crafted the research questions, we then ask the LLM to craft a research plan based on the question. By breaking it down into three steps, the LLM tend to perform much better. Another way to use prompt training is to apply prompt training with reflection. Prompt training with reflection involves self-reflection with the sequential steps to improve the LLM's reasoning and output quality, allowing the LLM to evaluate and refine its own responses. Here is an example. First, we ask the LLM to act as our chief legal officer and then review this SaaS contract for risk, focusing on data privacy, SLAs, and liability caps. And then we will pass in the contract contents to the LLM. Now LLM will first give us some concerns about this contract. Next, we can ask the LLM to draft an email to the SaaS product vendor outlining the following concern and proposed changes. And the LLM will then generate an email regarding the concerns of the SaaS product contract. At the final step, we can ask the LLM to evaluate the email that is written by itself and then give feedback on the tone, clarity, and professionalism. This is a very simple demonstration to showcase that prompt training doesn't have to be applied to sequential tasks. We can do some steps and then do some self-reflection on the quality of the previous response. Another example is to do plan and act. At times where the task we ask the LLM to do is complex and we are not an expert, we can ask the LLM to plan how to do for us, and then we ask the LLM to follow the plan to do it step by step. Okay, here is a demonstration of the workflow where given a task, we ask the LLM to plan and the LLM generates multiple subtasks, and then we conduct the subtask either concurrently or step by step. Once each subtask is done, we will merge the result of the subtask and then generate the final response. This is also another workflow called plan and act. The next one is a very important concept in LLM reasoning, which is the notion of train of thoughts or COT. COT prompt instructs the LLM to break down the thought process to enable complex reasoning capabilities through intermediate reasoning steps. The first introduction of train of thoughts uses these examples. It uses COT to solve a mathematical problem where the LLM is natively bad at. When we give the example of Q&A, if the answer is just the answer directly, the LLM at that point of time tend to give the wrong answer because we all know that LLM generates its response by guessing the next token rather than actually performing the mathematical calculation. But if we apply train of thoughts where we give an example such that the example includes the thinking steps, the LLM tend to perform much better because when it generates, it also generates the thinking steps. By implicitly ask the LLM to include reasoning steps, we are able to improve LLM's response more accurately. And there are zero shot and a few shot COT. For zero shot COT, typically we just use this magical phrase called let's think step by step or some other relevance or some other alternative phrase. The LLM will then generate its response in a logical manner, including the intermediary steps. If we give one or a few examples, essentially we are doing few shot COT. Here are some more examples of zero-shot COT. We can ask the LLM to perform certain tasks step by step, or we can ask the LLM to walk through your reasoning and so on. As if we are an expert of the task, we can also include further instruction for the LLM to follow our given steps without giving an example. That is a zero-shot chain of thoughts with steps. Finally, we can also provide multiple examples for the LLM to perform COT. Here is one example where we give the LLM multiple pairs, 4 pairs of Q&A to do the same task. And at the last step, we just provide the question and we expect the LLM to answer with the same format and same accuracy. Here is another example where if you want the LLM to perform some logical reasoning, we can give some examples of the question and answer pair where the answer includes step-by-step reasoning. Then the LLM will be able to solve the given puzzles in similar formats. The next one is self-consistency. Self-consistency is designed to upgrade on COT. The idea is very simple. Essentially, we ask multiple language models to perform the same task multiple times, and then we check which answers most consistent. That means it appears more frequently, and then we can take the most frequently appearing answer to be the correct answer. These simple, these very simple methods are actually widely used in LLM applications. Here is a simplified workflow where given a task, we ask the LLM to perform multiple inference independently. They use the same prompt and generates the same thing. And then for all of them, the results will be passed into another call, and then we find out which is the answer that is the most consistent, and then we will take that answer as the final answer. Tree of thoughts, another advanced reasoning model that LLM perform. Here is an illustration. Column A here represents the most simple way of inferencing, which we just pass the input to an LLM to generate an output. The second one is a chain of thoughts where we give the LLM some examples, the LLM logic in sequential manner. For self-consistency, we perform COT in multiple independent threads, and then we take the majority votes as the answer. And finally, for tree of thoughts, instead of doing train of thoughts independently, we take multiple steps, and for each steps, we will generate multiple options, and then we evaluate if any options are invalid. If it's invalid, we will kill off the branch, and then we will perform the next step. And we repeat until there is no more possible branches, and when it arrived at the potential output. This is a more complex reasoning model, which looks like how we think when we play chess. For each situation, there are multiple places you can put or move a chess pieces. For each movement, it will lead to certain outcome, and then we evaluate if the outcome is desirable or not. And some may take less steps to find out the outcome, and some may take longer steps. These tree of thoughts mimic how we think in a chess game in a tree structure pretty well. Here is an sample output of tree of thoughts. Let's say we want to solve a riddle of this: a man is found dead in a room with 53 bicycles, and how did he die? For the first branch, there will be one leading question: what could these 53 bicycles mean? And then there are multiple options. And the second branch will think, given these options, how do they interpretation? What's the interpretation related to the death? For option one, it will have an outcome. For option two, maybe there will be another outcome. And then how does each scenario fit with the rest? And then there will be analysis on option one, analysis on option two. And then we see that option one is quite unlikely to happen. This branch is killed. We will just keep the option two to be the conclusion. The prompt to trigger tree of thoughts is something like this. You ask the LLM to roleplay a detective to solve this mysterious case and describe simply how this case is like, and then instruct the LLM to solve in multiple steps. And then it will be able to follow instructions to think in for multiple possible outcomes for each step. There's also another effective zero-shot tree of thoughts prompts without giving too much instruction. We can attach this magical paragraph before the task, and this will trigger tree of thoughts process. Here, imagine three different experts that are answering the question, where this is the question. But all the experts will write down one step of their thinking independently and share it within the group. They will have a discussion. Then all experts will go on to the next step, etc. And if any experts realize it's wrong at any point, then they leave. That means we kill the branch. And then we leave the answer at the end. Empirically, this triggers tree of thoughts quite effectively. The next one is called REACT, which stands for reason and act. For the previous models, we do not allow the LLM to interact with the real world or the environment. The LLM just perform inference based on our instruction. But in actual cases, there are many times we will need to act as the human in the loop and provide feedback from the physical world. And here is the React framework that was introduced to help us perform such scenario better. React prompts LLMs to generate verbal reasoning traces and actions for a task. This allows the AI to receive feedback from external environments to incorporate additional information into the reasoning. This framework typically follow these three steps. It stands for thought, act, and observation. Here, there is a thought one, act one, and observation one. Then thought two, act two, observation two. And it will repeat until the LM thinks that the task is done. This is a typical response that is generated by LLM. A typical React system prompt looks like this. We ask the LLM to act as a system that is capable of reasoning and taking actions. And then we tell the LLM that your task is to answer questions by breaking them into steps. thinking about what you need to do and taking appropriate actions. We tell the LLM what tools they have access to, and for each step, we ask the LLM to follow these TAO formats. And then the LLM repeats until the final answer appears. The LLM will follow our instruction and has repeated series of TAO, thought, act, and observation sequence. Here is the break. It's 1 o'clock. The next part, we will talk about context. First, we look at the elements of the context. Ingesting context into prompt tremendously enhance quality of LLM's capability from general responses to take action. Typical elements includes meta instructions, past knowledge, tool use results, and memory, whether short-term or long-term. Furthermore, provide context is one of the simplest and most effective ways to tackle LLM's hallucination. The first thing is system prompt. System prompt is the overarching instruction to guide LLM's behaviors. Crafting well structured and meta instruction is generally given in system prompt. Let's look at what system prompt is. System prompt is the overarching instruction that guides LLM's behavior. Crafting well structured and clear system prompts empirically improve LLM's performance drastically. Each LLM comes with its default system prompt for optimal general purpose behavior. Crafting your own system prompt to optimize for your specific task. Here we can see that given a chatbot, the system prompt and the user prompts are combined together to be a single prompt to pass into the chatbot at any point of time. You can see here, each LLM apps come with its default system prompt for optimal general purpose behavior, and some LLMs allow you to craft your own system prompt. Okay, so what you're seeing here, this is an interface from Cloud, Anthropic Cloud, and this is an interface from ChatGPT that allows you to put in your custom instruction to the LLM in different formats. There are also some general principle in crafting system prompts. You may write the system prompt with this general information. First, you want the LLM to identify itself. That is very similar to the role play or the role assigned to the LLM. You want to provide some clear instruction that act as guidance to the model on how to generate response you want. You may want to provide examples of possible inputs along with the desired output from the model. And finally, you want to provide some context as any additional information that the LLM might need to generate a response, like relevant private or public data. Here is two screenshots of Cloud Opus 4.1 system prompt, which was released in September 2025. We can see that there are role assignments at the start and then current dates set at the start. And then there are some information and instruction on how Anthropic Cloud should behave. I won't go into detail. If you're interested, you can use this link to read through and get some inspiration. The total system prompt of Cloud Opus 4.1 is 2,562 words, which is very long. We can see that how important crafting system prompt is to guide the LM answer more usefully. Here are some key highlights of what the system prompt snippets of 4.1. First, it briefly states identity and product. Like it says the system is cloud and created by Anthropic. Then it encourages or restrict the behaviors of cloud. Say if people ask about the API, point it to the documents. If user is unhappy, I suggest pressing the thumb down button. This is waiting for users' feedback. It also has instruction to establish safety or moral restrictions. It asks cloud does not provide information to make chemical or nuclear weapons, and it restricts cloud to not to claim to be human or being conscious. It also states some facts. For instance, the knowledge cutoff of cloud is January 2025. And lastly, it instructs cloud to be human friendly, such as asking cloud to first think carefully before acknowledging if being corrected. Next is its tool use results. We have already introduced that when LLM is asked some mathematical task, LLM will decide if it should use some help from additional tools. Here it uses a calculator to calculate this mathematical operation and take the answer from the tool to respond to the user. And when the task gets more complex, LLM can use Pell to generate code and execute to get a more accurate response, and leverage a response to proceed to future reasoning. Another very frequently used tool is called web search, which appear in most, if not all, the popular LLM applications. We see here if the prompt does not hint a web search, LM can answer with its general in-context knowledge. But if let's say we use some keywords that hint LM to do search, like here, we ask the LM to check for me what papers are released in archive this week. All these are hints to trigger LM search. LM indeed perform its search on the website, and it will summarize the finding with the link to the sources to generate its response. Beyond that, there are many other tools. For ChatGPT, we can connect it to our storage. And for Gemini, there are deep research, Canvas, or video creation, etc. For cloud, it offers this protocol called MCP, which allows us to interact with many third-party tools very handily. Let's talk about knowledge and memory. The process of retrieving references from a knowledge base is often regarded as retrieval augmented generation, which we'll talk about in greater details in later lecture. The LLM search in a knowledge base, the LLM performs search in a knowledge base to retrieve relevant information to augment the original prompt. This process of The process of retrieving references from knowledge base is commonly regarded as retrieval augmented generation. The LLM performs search in a knowledge base to retrieve relevant information to augment the original prompt. This is a very typical process where text query is given by the user, and this will pass into the LLM. Instead of going directly to generate the response, the LLM will then perform a search in a knowledge base that we have processed, and then it will retrieve some relevant information to act as references, and then the references will be attached to the original query as context to augment and generate the response after that. Memory retrieval is similar. The memory retrieval shares a similar process, but the content is different. The retrieval is retrieved from a memory bank. Then there are two types of memory system, namely a long-term memory and short-term memory. Short-term memory typically refers to the dialogue history leading to the current utterance in the same conversation. And long-term memory refers to the user profile information that is extracted or deducted from all the past conversations and interactions between the user and the LLM. We can see the ChatGPT allows us to edit the memory saved. And of course, when we are paid user, the memory base size will be much larger. Okay, so now that we have found out what context is, let's take a look at some essential context engineering techniques. We've seen the common elements in the context, including the system prompt and user prompt. There is dialogue, history, and user profiles. That is part of the memory. There is a knowledge in the knowledge base. There's tool use results, and also there are reasoning steps that is generated by the LLM. So this information can quickly explode because there are so many things, and as the user's original query gets more complex, the information will be overloaded very quickly. The goal of context engineering is to prevent context explosion, and this is typically for the reason of limited context window, where all the LLM nowadays have a limited size of prompts that you can pass in. For ChatGPT, it should be about 400,000 words. And for Gemini 2.5 Pro, they should be able to take 2 million tokens at the same time. Also, this is done for cost optimization because the consumption of LLMs are based on input and output tokens. If we don't process the context, the input tokens will contain a lot of unnecessary contents that charge you unnecessarily. The typical context engineering actions can be taken is as follows. We will introduce some filtering technique, compression technique, and some multi-agents of techniques to help us improve the quality of the context. First, we introduce tool filtering. Here is the typical process, right? We pass in the query and then the LLM will select the tools to use. Then it performs the retrieval to augment the LLM and generates the response. First thing we can do is to add an agent that help us select the right tool to use instead of choosing all the tools available. The second thing to do is to have agents that help us evaluate which piece of context is more relevant or should be included, so that we don't have to pass all the context chunks retrieved from the tools. And finally, when the conversation gets longer, the context gets longer, we can ask an LLM to summarize the past context into history so that the context will not get too long. Next, we can perform context compression to summarize the older context from earlier dialogue into some context history, especially when this process has been going on for quite some exchanges. The context will tend to truncate very quickly. We can just ask a separate LLM to summarize all the context given thus far and put it into a single piece of history, and then we can continue the conversation without consuming exponentially growing size of context. Finally, we can attach the tool into domain adapted agents. That means each agent, or there will be a dedicated model that is specialized in handling a single tool. And then we use these agents to retrieve the information rather than using the tool itself to perform it algorithmically or analytically. This multi-agent approach to do LLM, to do retrieval gets more and more popular nowadays. Here is the end, and thank you for your attention.